Today we will pick up from the last time. So the last time we talked about the lateral torsional buckling of the case which incorporates the effects from the warping. So as we have the torsion, the warping is gonna happen if you are not dealing with the pipe or tube cross section. Then warping is gonna happen just like what I explained in the last class. So warping was incorporated. I showed you the equations and derivations in order to integrate the warping into the equation that controls the lateral torsional buckling. We substitute the boundary conditions. At the end we come up with the self-differential equation with the boundary condition enforced, and we get the moment m naught given in terms of the elastic modulus and other parameters as shown over here. So we're gonna use all of this information and continue in the class number 21. The lateral torsional buckling equation we derived on Thursday are based on this given format. The format I mentioned is this one. So it is under the condition that the moment apply on both sides and the beam is subjected to the uniform moment, bending moment. So the buckling was considered under this particular pattern of bending moment diagram. And the reason for that is the simplicity in the differential equation. So it is more convenient to solve differential equation having the simplified bending moment diagram like so. Okay, but the point is that you end up with this expression. It is just m naught. The point is that you really do not have just one case where the bending moment is uniform throughout. In reality, you confront with more complicated cases. Bending moment diagram could be anything. You have million possibilities, infinity possibilities. Well, so the way to incorporate the effects of the different bending moment diagram is by this introduction of the CB, where the CB is the constant that account for the bending moment diagram, the shape of BMD. This is what I covered already, that this equation come from, first we incorporate the vertical deflection. That is the EI about the x-axis that controls the deflection of the beam. In just the normal situation, if the buckling does not occur, you will not have the following three. But once you have the buckling, so when you lose the stability, you will have lateral motion. The beam is not intended to move laterally. It is intended to resist the gravity vertical load, and then you would suppose to have only just the vertical deflection. But this lateral deflection comes when it loses stability, and we derive all this expression from the deformed configuration, and we look into the deformed axis of the cross section of the beam. Okay, so lateral displacement comes in, and torsional deformation also comes in, as the top and the bottom of the beam will not displace equally, so the torsion is coming in. Then this torsion and lateral, they are actually they are coming in a package. They come together, and we use the lateral and torsional deformation and the governing equation for these two to cast for the instability of the beam. In some cases, like when we deal with the I-beam, this case you expect the warping to happen, and thus this torsion is causing the warping. So they are actually like the another package. Once we have the torsion, then the warping is also coming in, so they comes as a package. So we have all these four things and then cast them up into one equation. So you can see that it is a lot of difficulties. We have a lot of things going on in the differential equation, and we are not the one who developed. Those who developed back in 1960, 1950 or 70s, okay, they come into this simplifications. Okay, so CB will be coming in. Now the question arises, how was it done in order to really learn the effects from the lateral torsional buckling of the beam under the different shape of bending moment diagram? Because the BMD is not like this, and you said that, sir, you just mentioned that it is quite difficult or nearly impossible to solve differential equation for those cases where the bending moment diagram is not uniform like this. So how did the researcher or engineers in the past conduct the research or learn that learn how to come up with this CB constant? So the technique, or there are actually several papers published on this CB constant. Okay, so they focus on this CB, and the procedures used to study into the CB is the numerical technique. So basically, if you want to really understand this behavior, you can construct you can use finite element. Having finite element, then you can construct the steel cross section using the shell or the plate element. So you construct the flange, you construct the web, assemble them into Y flange cross section, and then you have the discretization in all three dimensions. So along the axis and along the X and the Y in the given cross section. Well, it is simple enough to study, to perform the research in this way, because the cross section, commercial cross sections, generally it is thin enough, so you can use the shell elements or the plate element. Actually, it has to be the shell. Okay, mostly you have the in plane behavior. The CB, if you look into AISC code, we are going to talk about the CB first. So if you look into AISC code gives you the provision that the CB, you can use the following cases. These are the simplest cases for CB first. So the first case, when the moment are applied on both ends into the opposite direction. So you can see that the moment here and the moment there are on the opposite. One is clockwise and another is in the counterclockwise. So this is the, this is the worst case scenario. You will not get the CB lower than 1.0. CB, the worst one, 1.0. So let's look into the effect. CB equals to 1.0, then you will get the moment critical being not greater than the M naught. Okay, so M naught is evaluated based on this case. So if you think about other cases like this, let me give you the picture. So I draw you this one. Okay, so if you end up with the bending moment diagram that looks like the red line, the severity of the case is actually less than the case where you have the green line, that the bending moment is constant throughout. So the more the CB is, that will reflect the case that you have less and less severities from the bending moment diagram you obtain. For the next case, for example, CB equals to 2.27. The bending moment diagram for this case is gonna look like this. Okay. So it forms a double curvature, and that results in the increase in the M critical to about 2.25 times as much of the original M naught. That's a big jump. Well, to be conservative, if you want to run the calculation at the end of the envelope, on the back of the envelope, or you just want to do something that you cannot rely on workmanship. For example, if you design those elements used in the deep excavation, for example, you will not use the large value of CB because you cannot trust the boundary condition. You are not so sure about the condition of the load, because the load might not be in this way, going to the same direction all the time in the real use of the structure. So the conservative way to use the CB equals to 1.0, well, that is going to work, and it is sort of a little sloppy for the design office. If you are too lazy and use just this CB equals to 1.0, sometimes you overuse the material. But for the temporary work, for the case that you are not so certain about the use of the structure, you are not so certain about the direction of the applied moment, because you might end up with so many load cases, then that will bring you back to the lower value of CB. And another case, which is given here, this writing was explained in the figure below. The last one is a case where you have the bending moment on one side and the other side was left free. So this case is given by the CB of 1.67, which is 5/3. Actually, for the first case, the cantilever beam is also counted in. So for a cantilever beam, you have the single curvature, of course, and wait a minute. So cantilever beam also applicable for the case where we use the CB equals to 1.0. Now let's take a look. Let's take a look at the AISC specification a little bit. So I take this picture, this page, let's say, from AISC specification 2016, which is free for the download. You have all of it. Just go to the page I mentioned. First of all, AISC, this is the chapter for the flexures. So first of all, AISC classify the cross section into the following types, so F2, F3, whatsoever, and then they talk about the compact or non-compact cross section. We talk about flange, talk about web, slenderness, criteria check, and the limit states for the failure of each type. Generally, we bump into the case where you have the top two cases like this. So sorry. So we come next to the provision. So the code allows you to use both using the strain reduction factor or using the factor of safety. This is the style for the latest AISC. You can see over here. For here, the phi, which is strain reduction factor, is used actually for the ductile failure, and this omega is actually the factor of safety. So you take the nominal moment and then divide by the factor, and then you end up with the allowable stress design. So this is a minor idea we have from the code. Next, the code suggests these CB values, and we're gonna elaborate on these CB values. We talk about this paragraph already. I crop and paste in that writing already, so I explain everything out. This is from the code. So let's take a look at the CB. The CB is given by look at this page. So CB is given by this number. Actually, if you take 2.5 plus 3 plus 4 plus 3, then you're gonna get the 12.5, like the numerator part. Okay, so I'm just going to put the frame of this. Not a perfect rectangular. It turns out to be trapezoidal shape. Okay, so we have this equation from AISC. It talks clearly that it is the absolute value. It is the absolute value. So regardless of the sign, okay, regardless of the sign, you take the absolute value. So I put in this page to make it very clear for us that we are talking about the absolute value of the moment. And how do we obtain all of that? So we take a look at this picture over here. This is a bad thing about teaching with the note that is pre-written, because I'm gonna be going very quickly. So if you cannot catch up, then go back to the YouTube that will be uploaded later, and then just follow that. So the M are determined from here. So we gonna get the M at the quarter of the length points. And what are these things? Basically, the question arises about the L. How do we determine the L? Generally, many cases, we'll find that the span length or the gravity support length are generally equal to the lateral support. Many cases, they are generally equal to. But the point is that the L in the code refer to the unbraced length, and the unbraced length is it is associated with the lateral bracing. So unbraced means without lateral bracing, okay, length. So for the case like this, it is easy for us to just pick up the L, but if you have the bracing in between the point, for example, between the gravity support, you also have the brace apply, that your L will be the new one, which is just here, not all the way through the entire span. Okay, so look at the definition a little bit before you use all these codes. The L will be elaborated probably in the other pages. So the CB over here is actually proposed by Kirby and Nethercott, and it is adopted in AISC specification. You can look into other codes or other provision like the BS. Let me go grab it. I think I have it somewhere. As soon as I teach, then I cough. Okay. I actually can give you the BS one, so I just need to move something around a bit. Yes, it is so packed. If we consider the BS code, the CB is given by, this is BS 5950. CB is given by M max. Actually, it's an absolute of M max. Divide by 0.2 M max. Oh, so, wait, 5. 1 second. This is a 12.5 M max. Okay, divide by 2.5 M max plus 1.875 MA, which is M1, plus 6.25 M2. Ran out of space. I think I just do it this way. I make American code bigger font. Oops, sorry. Plus 1.875 M3, and there it is. Put the absolute sign in there. So it is quite close. What is going on? Okay. Electronics. Not straight still. What do you want from me? Now it's not writing now. Okay. go for meditation sometime. I think if I can fight with iPad, that means the mental health is not in a good shape. Okay, this is the BS code. Right, whichever you want, or if you are the conservative person who gets scared of everything in the design, then you want to pick up the lower of these two. It's up to you. But well, maybe it's not that. Is it a good idea? Conservative side, well, it doesn't hurt. So, okay, you have some options to pick up the CB. So proposal from AISC, but generally you stick with AISC. Now we get the unbraced length, lateral unbraced length. We divide this span into 4 equal distance, or call it 4 length or equidistance, and then you define M1, 2, 3, 4, 1, 2, 3, because you have the L/4, a half, and 3/4, and you also have to pick up the maximum moment that appear within this span. Okay. Plug everything in regardless of the size. Again, told you this looks like empirical, but this comes from the finite element analysis. The researcher just run the parametric study. So they change the span, they change the type of the bending moment diagram, they vary everything until they are so certain that these relationships of the CB is good enough and conservative enough to be used in the code of practice. So that is just the parametric study. This don't ask why the 12.5 or so. It comes from the data obtained from several simulations. Okay, and then you drop in and it works. This is the equation that fits the base and will accepted around the world. Well, it is around the US. So this vertical support is not the criteria for you to use to pick up the unbraced length L. You need to look up to the lateral support. So this view is the elevation view. You can see the load apply, and then you see the bending moment diagram going on like this. But this is from the top view. So the plan view here is actually from the eyes looking down like this. So you can see the boundary condition that help restrain the horizontal displacement and also the twisting. Now the development we had so far, from here we get the equation from M0, you get the equation for the CB to incorporate the different bending moment diagram, and so on and so forth. It does not, up to now, we have not incorporated the effect from the location of the load. So the location of the load was incorporated by the study, these two studies here, Nethercott and Rocky, and Nethercott 1983. At that moment, well, I was just 1 year old. 1983. Okay, so let's see how does this work. The CB can be computed. So first of all, the CB above comes from the assumption that the load was applied, okay? The load is applied at the centroid of the cross section. Now, maybe we think about this fact. Load applied at the centroid of the cross section. How does it sound? It doesn't sound realistic. Generally, when you construct the steel frame using the wide flange cross section, you have the beam. How do you put the load? You put the load at the centroid? Well, in some cases, it might be. For example, if you have the plate welded to your web, and then this plate transfer the load from maybe the sub beam. Yeah? So you have the load acting right at the centroid. Okay, that is possible. But not likely. If you have the beam, you are going to put the you are going to cast the slab on top of the beam. You might put the hollow core, you might put the plank, whatever, right on top. Maybe the steel deck, composite, etc. on the top. So, when the load is applied to the location which are not right at the centroid, that also affects the stability of your beam. So that affects the lateral torsional buckling of your beam. So if we look at this case where the load is applied at the bottom, now you think of this one. I will sketch. So if the load is applied at the bottom, here we are. I cannot rotate the picture in GoodNotes 4. I'm not sure if GoodNotes 5 can do that, but I'm kind of having the dinosaur DNA a little bit in me, because I'm very used to the GoodNotes 4, and then I feel like I don't want to move to the GoodNotes 5. But I am pretty sure that there are many better things going on in GoodNotes 5. But the point is that I am a dinosaur, as I mentioned. So don't be a dinosaur. This is a bad habit. I don't recommend you to do this sort of thing. Okay, and you can see here, when the beam starts losing the stability, it starts deforming from the original configuration. So okay, maybe original. Okay, it should be somewhere here. So the original configuration is over here, and then when it loses stability, it goes to the left hand side. The buckling happens. So you can see that the top flange is moving more than the bottom flange. Yeah. And that causes the rotation of the entire cross section. My point is that the effects of the load, the location of the load, like this, what do you think? How does this affect to the torsion which is going on from the instability of the beam? actually the load that is applied at the bottom flange help stabilize the beam. It produces you the good effect, good behavior, because you apply load right down here. You are producing, if this is the centroid, so you are having the moment arm. This moment arm, along with the load magnitude, is going to produce this moment, and this moment is opposite to the lateral torsional buckling. So this one is the stabilizing moment. It affects in the good way. Okay. And then I move this out. Whereas this one, if we consider this picture instead, this is your original configuration, and the form configuration looks like this. So when it buckles, again, it moves laterally, top move more, bottom move less, producing the torsion, and then the load is applied that way at that location on the top. So if we look at the centroid and we find this moment arm and you have this force, so you find that force along this moment arm is going to produce the moment into the counterclockwise direction, and the beam is twisting in the counterclockwise direction beforehand. That means it worsened down the situation. So you have the more instability going on as you apply the load right at the top of the flange of the beam. I clean this up, then delete. Boom. Okay, so let's see how things are defined, because we're gonna use the number from the beam geometry for the definition of the CB below. Basically, the CB is given by these three variables. Well, 4 parameters. First is the A, is the B for a second, Y, and the D. The easiest one, the D. The D is the total depth. Okay, well, in the steel table they give you the H as the height of the cross section. So that's your D. A and B are to be figured out from the table that I will show you in the next page. So that is associated with the pattern of the load and the boundary conditions. Y now. Y is measured from the centroid, and the Y coordinates, the Y axis is pointing downwards. Well, you are familiar with this sign for the Y, right? So we are consistent to the very first derivation we did in the flexural problem. We define the Y to point downwards to pick up the deflection. X is pointing in the lateral direction, and and Z is along the axis. So as Y is pointing downward, Y is actually measured from the centroid of the beam. So at the centroid, Y is 0. You substitute 0 in here, you get 0 there. Then the B to the power of 0 turns out to be 1. So CB will be equal to just A only. Okay, if your Y value, if you apply load right at the centroid. Teaching just the course for teaching, one thing is the cough relief medicine. If I don't teach, I don't cough. If I teach, I cough. And to minimize the cough, I need liquid medicine to help the throat feel better, or maybe the fisherman's friends. This is the course for teaching. Okay, so it will be just the A. But if you have the location of the force not right at the centroid, you will get the effect from the B. So let's say the A accounts for how to make it easy to read. What is the size? Okay, this account for accounts for DMD, right? If the location is 0, then the only A exists, so that accounts for the BMD. The B accounts for the location. I shouldn't use red then. Okay, D is the depth. Oh, sorry, I was not consistent. I used the lowercase d up there, so I change it there. Okay. I don't need to do anything. The Y is given already, so Y pointing downwards, you get positive Y. Pointing upward, negative. Or this point, negative. Whatever below the neutral axis, Y will be positive. So for the centroid loading, the B turns out to be 1. Then CB is equal to A only. Bottom flange loading, if it is right at the bottom flange, then you substitute Y being D over 2. Y being D over 2, then that cancels out everything for the power of the B. So you'd end up with just AB. And if you have the top flange loading, then the power here turns out to be -1. So B turns out to be the denominator over here. So it produced the bad effect. Well, this is under the condition that the B has to be greater than 1. When the B is the denominator, then you end up with the negative effect. Okay, so this is the multiplication. CB comes from the multiplication of these two. So if you want to be more precise, then grab this to use for the calculation of your CB. But still, for the design point of view, well, in the checking point of view, it might be worthwhile to come to this point here. But for the design point of view, this might suffice your purpose. If this one gives you more severity, then you might opt for this one. And in fact, the part that accounts for the bending moment diagram here for the A actually existing, right? Because the CB proposed above accounts for only the shape of the bending moment diagram. So that could be, this is, well, not, let's say, officially published, but the idea is just two terms like this. So we should be we should be, we have the eligibility to use the A to be some of these terms, okay, from the calculation above, and then you account for the location in the B terms. Okay, so let's go look at the table for the A and B. Look at the table. The first table, all these tables are coming from this. It is a Structural Stability Research Council, SSRC, and they proposed and told you this must be from the finite element analysis. So the beam should be constructed in a numerical model. I think we used to have the beam picture like this. Anyway, you just don't want to go grab it. This should be enough. And then oh, I have more than one line. Okay, guess it is right at the center, and then I copy this part here. Just want to illustrate you a little bit. It's just a picture of how things were done. This one, copy and paste. So the three-dimensional finite element analysis model could be constructed just like this in order to study the instability effect of the beam under lateral torsional buckling. I mark it here first, and then delete this, and then draw the line to here. Okay, there it is. So construct finite element model. You know, when I edit the video, that one thing, one pain, I have to remove the sound of throat clearing. So that takes a lot of time to edit the video. You have no idea how much work done in order to get one video published. I mean, my work done, okay, on YouTube. Not talking about those celebrity on the YouTube, because that is for profit. Oh yeah, this is stupid. I should copy this. Yeah. So yeah, a few hours has been used to clean up my the part that I was maybe freezing. The brain might not function at the moment in the video, and then I need to remove all those things out to make sure that we have a nice and clean YouTube. Alright. Then there it is. So I am showing you the discretization. One second. Not good. Okay, and then the next one, sort of chip. Okay, this line I remove, just a bit. Don't worry, we have so much time. I accelerate a lot at the beginning already. Why don't you just enjoy this with me? You say you don't want to enjoy this. I waste your time. Okay, these things are going to repeat. Give me 1 minute. It's gonna be fast now. Copy and paste. Okay. Good. This will be delete. This will be delete. This will be copied and will be paste like this, and will be paste like this, and will be paste a little more, a little more, a little more. Okay, looks good. So what next? Another line, another line. Then delete this one and copy this one and paste. What? Okay. And paste and paste and paste and paste and paste. There it is. I really wonder why should anybody hire me in the next year? Having all of this done. Well. Okay, now the FEM model actually might be discretize better, but we're gonna have the finite element model. Constructed in order to study of this. So you can put all the restraint if you want. Okay, I told you I should go for the meditation. I fight with iPad. The monk will say that I will need some peace of mind. Well, okay. You can put the boundary conditions, the support that reflects the reality. The screen is jerky when you write and move the page, but the sound is still good. Well, let's see. I think the quality of the screen might not be as good on the Facebook, but on the YouTube, I think we have no problem. So just forget about this. I really cannot improve. Let's say I cannot improve the broadcasting quality. So we might just look into this, into the better quality video, better quality video on the YouTube then. All right. I think I cannot help improve this issue now on the Facebook Live. So and when I edit the video, then I gotta cut a lot off. So when you look back at yourself talking or teaching, you're gonna find that there are so many things that look sloppy. You may not like it. And this one, this is missing. Oh no, oh boy. Okay. That is boundary condition was imposed. And wait, what I did? Okay. Precise boundary condition was imposed. I will not write it down. Full thing was imposed, but want you to understand that this is what it takes for people or for the finite element engineers. Well, not FEM people. It's actually the still people who use finite element. So precise boundary condition must be applied. Okay. Second, precise load location is also the case. Thus, you will be able to do all the things you want in the finite element model. Basically, if you want to apply the vertical load, you want to study apply at the top flange, that is possible. Because finite element takes care of everything, but the point is that you are not getting the closed form solution. Who cares? Getting closed form solution, right, takes you so much time, or not possible, then we go for the FEM, and then we fit the curve. That's it. Not we, they. Okay, so location was taken care of. The shell elements use were used. The last thing, in order to study the lateral torsional buckling, you need to turn on the second order effect, has to be incorporated. So the geometric nonlinearity will be taken care of. This is the requirement for the finite element model for the study for the CB. Actually, for quite many things in this steel business, because you cannot afford to run the test program. That test program means physical specimen testing in one program that covers all cases you might need to learn. You will be having hundreds beams in order to construct the data point or the relationship or the function or the curve. You need numbers of data points, and you imagine testing like hundreds beams. It is not going to make one PhD graduate within 4 or 5 years. It's going to be quite very long time, and the instrumentations in the physical specimen testing is actually not an easy job. So the beam, if you test it this way, then a bunch of instrumentation going on. Sometimes the test result, you put up the boundary condition not so accurately, because the stability issue, it is very sensitive and it is very quick. So in a moment, then your beam just buckle, and if you miss some little minor detail, then you get the information or the capacity or the result of response, which is like so much different from another counterpart model that is done better or more precise. We do not see a lot of physical specimen testing of the steel structure in our structural engineering laboratory at AIT. Actually, in Thailand, we do not test. We can name just a few researchers, the faculty members in some university in Thailand who do the research in steel, but that's just a small number in comparison with concrete people, because the construction around here, we use more concrete than steel. Steel is more expensive in the country like this. Like this. Well, what is like this? Like this means developing country, okay, to be precise. For the USA, for Japan, for European country, they use more steel because steel take less construction time. And the construction time, as a matter of fact, the cost for them, the big piece or the big proportion of cost for them, because the labor is much more expensive than this area. And concrete, we have the limestone mountain, so we can produce as much concrete as we want, and we give out the CO2 emission as we want as well. Well, anyhow, that's why we don't see much research or physical specimen testing of the steel in laboratory in Thailand. This video is not intended to just for the people in Thailand to watch, but anyhow, I'm talking to the student mainly that why we don't see much. Actually, we don't see at all the steel structure testing in the laboratory here. But if you look into the literatures of the steel testing, since I'm from Austin, I have seen, not at the laboratory, of course, I never stepped into Ferguson lab for an entire 4 or 5 years when I was there, which I told you already that is the most stupid idea, most stupid thing I ever done in my life, because later on I need to test a lot of things, and I should have learned a lot from Ferguson lab if I step in there and take a look a little bit to get some idea. But anyhow, we have seen, actually we can see a lot of steel specimen testing from the publication, and the quality of the test that includes mainly the way the load is applied, because if we are looking into the concrete structure lab, we apply the load, and many times we are not so serious about the loading point. But for steel structure, those people are very serious, and the loading points is made of the knife edge sort of loading point to make sure that the boundary conditions and the load is identical to the finite element model, and it affects seriously. And likewise for the support conditions, that's also mimic all these things you see in the FEM. So pin is pin, roller is roller. It is very precise. The setup, the alignment setup, the specimen setup is another level. I would say it this way. It is another level. So RC structure, you have so many things that affect, and ultimately those that affect and the quality of the setup might not, you might not be able to differentiate. But I do not encourage you to make sloppy specimen. Okay, I'm saying this. I'm trying to tell you that it could hardly be seen that the result that is not perfectly matched with the calculation or with the FEM might be from many sources. Just the concrete alone in one beam, you cast concrete, maybe you need 2 mix. So 2 mixes, you could end up with 2 different compressive strength. Of course, you say that you measure everything well, you mix everything well, you do everything in the identical way, so you would suppose to get the identical compressive strength. But no, that never really happened for concrete. You have no idea the rocks or the coarse aggregate used in the previous batch and this batch are having the pretty much the same aggregate size or not. Sometimes you show it from you get it from the bottom of the pile, the stockpile, whereas another batch is taken from the the surface of the stockpile, the size could be different. So many uncertainties in concrete testing, and because of that, then the physical testing of the concrete specimen is then sort of relaxed because people gave up, whereas the steel specimen testing is going to be more stringent. Talk too much. Okay. Anyhow, I think you get the idea how you come up with this. Before we get there, further into this provision, okay. Right now the code talks about many things in the lateral torsional buckling, but let's talk about the concept first. Is I believe any axis? No, not yet. Okay, that's a scratch pad. Well, here. Let me. So this is a case study for you. As long as you are in the school, just go take a look at everything. Something you might not be interested in at this moment of time could be very useful for you in the future. So especially for those of you who are not living in Thailand and you just stay here for a given time period, and it is difficult to come back to see what you might want to see in the future. So whatever is available for you to see, just take a look at them and try to learn as much as possible. Don't set up or don't have the mindset on something and think that you will never use it in the future. You might end up needing it in the future. L over Y. We are going to write down the relationships between the critical moment to the plastic moment in the vertical axis versus the L, which is unbraced length. The unbraced length over Ry. Why do we talk about Ry? And I should speak up. Because we are talking about the lateral buckling, lateral torsional buckling. So the parameters, the properties of the cross section that affect the buckling, lateral buckling to be precise, is the one that control the lateral movement. So IX is the major axis, I value. Of these are given in the steel table, whereas the IY is the minor axis, I, and the IY is controlling the moment the flexures about this axis. The y is controlling this lateral, where the x is controlling that vertical deflection. Which is stability control. For x, nothing to do with the stability. So the Iy is the one that control, and that results in the Ry that appear over there. Now, let me borrow the line here. Paste it. Basically, it is like column. When we consider the column, the cross section control the capacity of the axial force by the maximum possible number you can apply is the A times the Fy. So the material nonlinearity controls the capacity, and likewise for the beam case, we have I want to cough. The yielding of steel is going to control the capacity of the cross section. So no matter how much the elastic buckling strength could be, you cannot exceed the material property that controls the yielding. Okay, so oops. I need more fisherman's friends. Difficult to get out to buy something. Anyway, you cannot complain. Neutral axis is here. So let's look at the limit states of the steel beam under flexures. First, you might have small moment. Oh no, okay. Later on, it gets heavier. So the moment, I'll explain point by point. And then I will explain you. Wait a bit. So we have several limit states of the beam and the flexures. Okay. Okay. Whatever. We start from the green one. The green one, we apply moment. The moment is still smaller than the my. So this is the elastic moment. The stress here is less than sigma y. So the M is less than my. The current moment is less than my. The next step, once you produce the big enough moment, we have we define this as this is sigma y, and you have the my. The my is the onset of the yielding. Yielding starts at the extreme fiber first, and then it spread in. And as it spreads in, you see this picture. Oops. As it spreads in, this, and this. So the stress could not be greater than sigma y. If we look at the strain diagram, plane section always remains plane. So strain diagram is gonna look pretty much like this. And at the point here, you exceed, which correspond to this and this, you exceed the epsilon y. So once you exceed epsilon y, you cannot get anything more than sigma y. Just that. Same over here. Okay, I clean this up. I will not keep it. And the yielding spreads from the outermost layer to the inside. So this M is greater than my but less than mp. Basically, the my and mp are not that far. We actually can do something with it, or can find it out. We can draw the moment curvature response, and well, you will see. Sigma y, right now it is the mp. Plastic moment. Plastic moment means you have the entire cross section yielding. So you apply large enough curvature that makes your strain hits the yielding from pretty much from here, but actually in reality your beam will not undergo that large deformation. So to be able to mobilize the sigma y at both corners. If you look into the moment curvature response, this is what you get. It is sort of like back to school. Many of you are still working from home now, and then many of you are not the current student, graduated for many years, still watching, which is good. I always tell the people in the next generation, like, don't stop. It does not mean if you graduate, if you receive the diploma and you should be stupid at that moment. You learn a lot, a bunch of homework, a bunch of practice assignments, and so on. And then you graduate, and then you just give up to be smart, and you turns out to be stupid after the graduation. The knowledge decays very quickly. If you look at the rate of decay, it is the exponential decay. It decays very quickly in the within the 6 months after your graduation, and you'll be completely stupid because you forget completely almost everything. Before I went to the US, I actually worked for a short period of time. I didn't work in the structural engineering. I worked in that airport thing, figure out if the Don Mueang Airport should be operating or what should be the activity to be done when the new Bangkok International Airport, Suvarnabhumi, is open at that moment. So I didn't do anything about structural engineering for about half a year, and then I went to the US to study, and then I know that I was that time stupid. I forgot almost everything. I mean, it is not a complete forget, but things are not handy. Things are not handy. This is the moment curvature response of the cross section, and it might be two cross section. So you can play it. You can play it, really. Try it. I don't think this is difficult to do, and you may not need my instruction to produce the moment curvature response of the steel cross section. If it is concrete cross section, okay, I can understand that there are something that I should talk about. But for steel cross section, you just have compatibility. You just keep changing the phi values, and then you will get the moment. You get the moment, plot moment, and phi. So I don't think that I should elaborate on this little detail, but I'm gonna show you the picture. Well, I think I normalize this such that it is possible to plot several responses in the same graph. First of all, as I use the normalized axis m over mp and phi over phi y. Okay. Yeah, that should be that. So this number is 1.0 for m over mp. MP is not military police, it is plastic moment. I will need the vertical dot. Tuesday you don't have anything. Tuesday you have only my class and Dr. Thanakor's class in the afternoon. So overtiming, actually it is a bad habit for Japanese. I know Japanese professors are very serious about the overtiming. If I teach in the room that the Japanese professors are going to come in after, then I was very worried if I'm going to overtime and leave the room for too late, right? Or even without anybody coming after. They respect the schedule, like the train schedule, every schedule. Okay, they give they pay good respect to that. So bad. I am not respecting your schedule now, so I keep teaching. Actually, I used to tell people that you don't need to respect me. I teach you, but I'm not the role model. I'm not different from you. So don't respect too much. And it is good not to be a respectful person. So life will be more relaxed. Maybe you don't get this, but one day you will. The more you are respectful, the more pressure on you, like, oh, you got to be always forget about that. First of all, so we have the moment curvature response of the line, two lines. Two lines are from two different cross sections. No, ugly. Let me change this one. It has to be higher. Okay. And then the curve is not gone. Come on. Okay, beautiful. When you plot the moment curvature response, you can end up with the different behavior pretty much like this. First of all, when the normalized ratio of the phi to phi y approaches 0, we are talking about two different cross sections now. The red line and the purple line. The purple line is this cross section, whereas the red line is for the y flange cross section. Paste and resize, and I need the color to be red, or that red, and that's it. Oh, come on. Oh, gosh, what? Just gone? Damn. Color red, not that red. Resize. That's it. Okay. The behavior of the y flange cross section is pretty much like bilinear behavior. It can be simplified. I should say it this way. Can be simplified using bilinear behavior or bilinear model. That is elastic, perfectly plastic. You know, one good thing about the class, we forget about the coronavirus for a moment. You don't think of that when we learn something in the class, when we're taking the class. Why are these two different? Once you hit the yielding, the first the yield curvature, then should define the curvature, right? My advice is going to be waiting, but still okay. Yeah, 10:30. They can wait. Well, we can (1.0) is this state. Okay, when the extreme fiber hit the yielding. The point is that the cross section, if you are talking about the wide flange cross section, in comparison with this one, talk about this one first. But this one, first of all, the yielding is at here, right? And then the yielding spread down to the centroid like this. Whereas for the wide flange cross section, the yielding starts at the extreme fiber as well. And in a few moments, so you just apply a little bit more than phi y. The entire flange yields. And as the entire flange yields, the flange is actually contributes pretty much the most for the to the capacity of the wide flange cross section. So you can see that first yield of this surface, and in a bit you have the complete entire thickness, flange thickness yielding. The web yielding is just the source. It is for Thai people, we call it is just a sauce. It is like a sauce that you dip. It is not the food. It is not the main thing you eat. It is just the dipping sauce. So we can just neglect or disregard the effect contributes, or the capacity contributes by the web, right? So 95, 99% is achieved somewhere around here, and then later on you gain a little bit more from the web. Whereas this one, once it starts yielding, then it progressively spread, right? So this part here in the middle still contribute and increase the capacity slowly until you achieve the full cross-section yielding. Okay, so here is the mechanics of the flexural member limit state. This moment here, you still talks about SX. And beyond this point, after the yielding and all the way to here, now you talk about ZX. The SX come from M. Oh, okay. SX come from sigma equals to MC over I. You know this. So the in order to make it easy for you to determine the M, then you have the sigma times the I over C, where C is measured from the extreme fiber to the centroid, and that is the definition of the SX, the section modulus. Well, we're gonna continue tomorrow. So I will talk about the behavior we will obtain over here, and that will constitute the building code, the design code. So you're gonna look at these things and ties up with what we derived previously. Okay, so good enough for today. We gonna meet again tomorrow. Bye bye, have a good day.